In this lecture, we consider the topic of right and left-handed limits. Okay, these are related to the type of limits that we've been doing up until now, which, if you want to differentiate, are called regular limits as opposed to directional limits. So, directional limits. Okay. So here's the idea. When you want the limit of f of x at x is equal to x naught, what we're doing is we're saying, well, as x gets closer and closer to x naught, what do the function values look like? Do they tend towards a particular number called the limit? Okay, so you can imagine that you've got an interval centered at x naught, which goes from x minus delta to x naught, sorry, x naught minus delta to x naught plus delta. And you have to throw away x naught because we never take the function value at x naught. So on that set, which can be considered to be the union of two open intervals, from x naught minus delta to x naught, which is to the left of x naught, and the union with x naught to x naught plus delta, which are points to the right of x naught, at up to a distance delta from x naught. We don't include x naught itself. And we imagine getting this delta smaller and smaller. So on these shrinking intervals, we are asking what are the function values, and do the function values f of x for x within these intervals, are the function values tending towards a particular number which we call the limit. Now, I might also have a reason to consider these intervals by themselves. And I might ask, okay, just on the interval x naught to x naught plus delta, or on the interval x naught minus delta to x naught, just on one of those intervals, what do the function values look like? And are they tending towards a particular value or not? And it turns out that the answer to that question can answer, uh, can give you some information can tell you something about the regular limits that we've been considering before. Okay? So here's a diagram that I took from Wikipedia. And so we have a function y of x. It's graphed on the xy plane. We're considering the value of the function and its limits at x naught. So at x naught, the function value is 0, and the graph of the function is in two pieces. So now, if you were considering an interval from x naught minus delta to x naught, excluding x naught, and so you're considering numbers that are to the left of x naught, and I asked you, uh, what's the limit of the function? So you follow the graph along, and this lower red circle, the height of that lower red circle would seem to be the limit at x naught for this function. The actual function value is 0, and the limit value is the height of this lower red circle. Now, if I was considering numbers x naught on the interval from x naught to x naught plus delta, and I'm traveling along the graph, and then the values would be tending towards the height of the y value of this upper red circle. So the limit itself doesn't exist. We've seen that before because on if we consider the values on both to the left and to the right, we're getting different numbers, right? The values would not be settling down to a single number. But if you were going from the right, the function values would be tending towards the height of this red circle. And if you're coming from the left, the function's values would be tending towards the height of this lower red circle. So the left-handed limit exists. It's the height of this lower red circle. The right-handed limit of f of x exists. It's the height of this upper red circle. And the function value x naught is neither of those. Okay? And the regular limit does not exist. Okay? So this is the notation that we use. We write limit as x goes to x naught, and we write a superscript plus sign. So we read this as the limit as x goes to x naught from the right of f of x is equal to L when, as x gets arbitrarily close to x naught, taking values that are greater than x naught, but never equal to x naught, then f of x takes values arbitrarily close to L. Okay. Similarly, for the left-handed limit, you're approaching x naught from the left. So this is read as the limit as x goes to x naught from the left, right? From the left is shown by this superscript minus sign. The limit as x goes to x naught from the left of f of x is equal to L means that as x gets arbitrarily close to x naught, taking values less than x naught, but never equal to x naught, f of x takes values arbitrarily close to L. Okay, so let's do an example. Supposing you have a function which maps reals to reals and is defined by f of x equals 1 for positive x, and it's equal to 0 otherwise. And so there's a jump in the function values at 0, right? And the graph comes in two pieces. Okay. Now, what are the directional limits? Well, the limit as x goes to 0 from the left of f of x equals the limit as x goes to 0 from the left. So when you're considering negative values, then the function value f of x is 0. So that's the limit as x goes to 0 from the left of 0, which is equal to 0. The limit as x goes to 0 from the right of f of x equals the limit as x goes to 0 from the right of, when x is positive, then f of x takes the value 1. So it's the limit as x goes to 0 from the right of 1, which is 1. Okay? So the directional limits exist, and the regular limit does not exist, because if you consider numbers very close to 1, both to the left of 0 and to the right of 0, you'll keep getting these two different values, 0 and 1. Right? Okay? Alright, so here's some we'll consider the relationship between the directional and the regular limits. Okay? If the directional limits exist and are different, then the regular limit does not exist. Okay, that's what we just saw in the previous example. Right? So, as the limit as x goes to 0 from the right of f of x is not equal to the limit as x goes to 0 from the left of f of x, the regular limit as x goes to 0 of f of x, does not exist. Okay. Supposing that the regular limit exists, then what can we say about the directional limits? If the regular limit exists at x naught, that is, the limit as x goes to x naught of f of x is equal to L, then the directional limits do exist, and both of them are equal to L. So, for example, the sine and the cosine functions They're continuous, which means that their limits are given by just considering the function values. So the limit as x goes to pi over 4 of sine of x is just sine of pi over 4, which is 1 over root 2. Okay, since the regular limit exists, the two directional limits must also exist at that point, and then they must be equal to the regular limit. So the limit as x goes to pi over 4 from the right of sine of x is equal to 1 over root 2, and the limit as x goes to pi over 4 from the left of sine of x equals 1 over root 2. Okay, now let's consider the case when the directional limits exist and they are equal. What can we say about the regular limit? If the limit as x goes to 0 from the right of f of x is equal to the limit as x goes to 0 from the left of f of x, let's say, so these limits exist and they're both equal to the same number L, and then the limit as x goes to x naught of f of x is equal to L. There's a misprint there. That should be the limit as x goes to x naught of f of x is equal to L. Okay, so for example, consider f maps reals to reals defined by f of x equals x squared for x non-negative, and it's equal to minus x for x negative. Okay, we want to consider the limit at x equals 0. Well, the limit as x goes to 0 from the right of f of x equals the limit as x goes to 0 from the right of x squared. Now for positive x, the form of f of x is x squared. So the limit is, this would be the limit as x goes to 0 from the right of x squared, which is equal to 0 squared, which is equal to 0. If you take the limit as x goes to 0 from the left of f of x, so those are negative numbers. When you have negative numbers, then f of x has the form minus x, the way we've defined f. So this is the limit as x goes to 0 from the right of minus x, which is equal to minus 0 equals 0. So the directional limits exist, and they are at the point, and they both equal at that point. So the regular limit at that point exists and is equal to the two directional limits. Okay. Now, what about when a directional limit does not exist? So if one or both of the directional limits does not exist, then the regular limit does not exist. Okay, so we consider a function f maps reals to reals. It's defined by f of x is equal to 1 over x for positive x, and otherwise it's defined as minus x. Okay, so if we consider the directional limits, the limit as x goes to 0 from the right of f of x. So for positive x, f of x is equal to 1 over x. So this is the limit as x goes to 0 from the right of 1 over x. Then we've already discussed that. That does not exist. Okay, the other limit, the limit from the left, does exist. The limit as x goes to 0 from the left of f of x. When x is negative, f of x has the form minus x. So this is equal to the limit as x goes to 0 from the left of minus x, which is minus 0 is equal to 0. Okay. Since one of the limits, directional limits, does not exist, the regular limit at 0 does not exist. Okay. Now we consider the case when directional limits exist but are not equal. Okay, we've already done that. The regular limit, then the regular limit does not exist. So for example, f maps reals to reals defined by f of x is equal to x squared plus 1 for non-negative x, and it's equal to minus x for negative x. Okay, and we consider the directional limits at 0. If you take the limit as x goes to 0 from the right of f of x, then you're talking about positive numbers. And for positive numbers, f of x equals x squared plus 1. So the limit as x goes to 0 from the right of f of x equals the limit as x goes to 0 from the right of f of x equals x squared plus 1. That's equal to 0 squared plus 1, which is equal to 1. Okay. The limit as x goes to 0 from the left of f of x, well, now you're talking about negative numbers. And then f of x has the form minus x. So this is the limit as x goes to 0 from the left of f of x equals the limit as x goes to 0 from the left of minus x, which is minus 0, which is 0. So both directional limits exist. The directional limits are different from each other, and so the regular limit does not exist. Okay. It turns out that if you're talking about regular limits, sometimes you can apply what we call the squeeze theorem, and for directional limits, there is also a version of the squeeze theorem, which we will consider next.